In linear algebra, real numbers are called scalars and relate to vectors in a vector space through the operation of scalar multiplication, in which a vector can be multiplied by a number to produce another vector. More generally, a vector space may be defined by using any field instead of real numbers, such as complex numbers. Then the scalars of that vector space will be the elements of the associated field. A scalar product operation not to be confused with scalar multiplication may be defined on a vector space, allowing two vectors to be multiplied to produce a scalar. A vector space equipped with a scalar product is called an inner product space. The real component of a quaternion is also called its scalar part. The term is also sometimes used informally to mean a vector, matrix, tensor, or other usually compound value that is actually reduced to a single component. Thus, for example, the product of a 1A, n matrix and an n 1 matrix, which is formally a 1A, 1 matrix, is often said to be a scalar. The term scalar matrix is used to denote a matrix of the form Ki where K is a scalar and I is the identity matrix. Etymology: the word scalar derives from the Latin word scalaris, an adjectival form of scalar. The English word scale also comes from scalar. The first recorded usage of the word scalar in mathematics occurs in Fr in a section via Te's analytic art. Magnitudes that ascend or descend proportionally in keeping with their nature from one kind to another may be called scalar terms. Latin: magnitudines curie ex genere ad genus sue vi proportional iter ascendunt vel descendunt, vocentur scalars. According to a citation in the Oxford English Dictionary, the first recorded usage of the term scalar in English came with W. Hamilton in 1846, referring to the real part of a quaternion. The algebraically real part may receive, according to the question in which it occurs, all values contained on the one scale of progression of numbers from negative to positive infinity. We shall call it therefore the scalar part. Definitions and properties. Scalars of vector spaces equals, a vector space is defined as a set of vectors, a set of scalars, and a scalar multiplication operation that takes a scalar k and a vector v to another vector kv. For example, in a coordinate space, the scalar multiplication yields. In a function space, k is the function x a k, e, x. The scalars can be taken from any field, including the rational, algebraic, real, and complex numbers, as well as finite fields. A number by the elements inside the brackets equals scalars as vector components equals, according to a fundamental theorem of linear algebra, every vector space has a basis. It follows that every vector space over a scalar field K is isomorphic to a coordinate vector space where the coordinates are elements of K. For example, every real vector space of dimension n is isomorphic to n-dimensional real space Rn. Scalars in norm vector spaces equals, alternatively, a vector space V can be equipped with a norm function that assigns to every vector V and V a scalar V. By definition, multiplying V by a scalar k also multiplies its norm by k. If V is interpreted as the length of V, this operation can be described as scaling the length of V by k. A vector space equipped with a norm is called a norm vector space. The norm is usually defined to be an element of V's scalar field k, which restricts the latter to fields that support the notion of sign. Moreover, if V has dimension 2 or more, k must be closed under square root, as well as the four arithmetic operations. Thus the rational numbers q are excluded, but the surd field is acceptable. For this reason, not every scalar product space is a norm vector space. Scalars in modules equals, when the requirement that the set of scalars form a field is relaxed so that it need only form a ring, the resulting more general algebraic structure is called a module. In this case the scalars may be complicated objects. For instance, if R is a ring, the vectors of the product space Rn can be made into a module with an R, n matrices with entries from R as the scalars. Another example comes from manifold theory, where the space of sections of the tangent bundle forms a module over the algebra of real functions on the manifold. Scaling transformation equals, the scalar multiplication of vector spaces and modules is a special case of scaling, a kind of linear transformation. Equals scalar operations equals, operations that apply to a single value at a time. Scalar processor. See also, scalar. References. External links, Haswinkel, Michiel, ed., Scalar, Encyclopedia of Mathematics, Springer, ISBN 978-1-55608-010-4, Weierstein, Eric W., Scalar, MathWorld. Mathwords.com. Euroscalar.